Hey, welcome to Ones and Zeros. My name is Ben, and today we are doing another video in our STM32 Basic series. Today we're going to do something a little bit different, and rather than looking at a particular peripheral or something like that, we're going to be looking at the overall architecture of STM32 chips, specifically the bus architecture, and have a look at how the different parts of the chips are actually connected together in order for them to function the way they do. So when you're doing programming with any chip, whether it's an STM32 microcontroller or any particular computing system, it's really handy to have a bit of an understanding of how the various parts of that system come together in order to be able to best leverage how those work together. So how to get the best performance out of a particular device or system. So what we're going to be looking at today is how the bus architecture works, but not just for one particular device. We're going to be looking at a variety of different devices. So some of the ones that I use regularly, and have a look at how the smaller and the larger variants of different STM32 families all kind of operate and how their pieces connect together, what some of the differences are between the various family members, and get a bit of an idea of the way that all works. So what we're going to jump to is this screen here. So this is one of the data sheets this is actually for the STM32F429 RE, which is the chip that is on the Nucleo 64 board that we typically use for this video series. And we're going to look at that one first up, just because it's the one that we most commonly use. So let's just so that we can see the particular one that we're talking about there. That's this little guy here, which some of you will probably be familiar with. So in the data sheet, there's typically two main documents that you're going to find for each of the actual chips. One will be the data sheet or the specifications document. I typically refer to it as the data sheet, and then there'll also be a reference manual which contains way more in-depth details of the various peripherals and their various registers and things like that. In the data sheets for the various devices, which I've got a few of them open here, which we're going to have a bit of a look at, they do have a diagram in them of the actual internal architecture of the chip and how the various components are connected together. So this one's on page 15 of this data sheet for this device. And we can see that from the diagram, it's sort of showing, we'll zoom in a little bit if we can. There we go. We can see the diagram of all of the various peripherals and the buses and things that connect them. So we'll have a look at sort of some of the common things across all of the devices, which is typically in the diagram, upper left-hand corner, you're going to have the actual CPU itself. In this case, we can see we've got an ARM Cortex M4. It's got a maximum of 100 megahertz clock speed, and it contains an inbuilt floating point unit or FPU. And we can see that's actually got a few different connections over to a AHB bus matrix, which allows it to connect to various other parts, and you're typically going to find most of the higher speed parts are connected to the same bus matrix that the CPU is connected to. So in this case, we've got the 0.5 megabyte of flash memory is connected to that one. We've got our 128K of SRAM is connected to that. We've got both of our DMAs, so DMA1 and DMA2 connected to our bus matrix. Another connection for our USB full speed peripheral. And then we've also got a connection to our AHB1, which we can see there is also clocked at 100 megahertz. So most of the higher speed stuff is going to be connected to the bus matrix. The bus matrix itself allows various different ports to connect to various other ports. So there'll be some master ports which can request data from a slave port, or they can send data to a slave port. So we can see here it's got 7S4M, which is letting us know that this particular bus matrix has 7 slaves and 4 masters. We've got the 3 connections from our CPU. One is for data, which is our D bus. One is for instructions, which is our I bus, and then we've also got an S bus as well. We've got 2 different connections to our flash memory. One to our SRAM, and then one each to our DMAs, the AHB1 and AHB2. Now, the AHB part is basically the AHB bus, or AH bus, is a particular type of bus that was developed by ARM in order to allow its technology to interconnect with various other bits of technology. So it actually stands for Advanced High Performance Bus, and typically going to be looking at a bus that is 64 bits wide or more. It could be 128 or 256 or higher, and that kind of represents how much data can fit down the bus per clock cycle. So we can see the 2 AHBs here that we've got, AHB1 and AHB2, are both running at the same speed as our CPU, or able to run at the same maximum speed as the CPU's maximum, so up to 100 megahertz. And we've got AHB1, which then goes down and connects to our AHB to APB2 bridge and our AHB to APB1 bridge. And those then connect off to APB1 and APB2. So the APBs are advanced peripheral buses, and it's another type of bus that ARM has developed, which allows peripherals and things to be connected. It's less advanced than the AHB, typically 32 bits wide, so can't fit as much data per clock cycle, but perfect for being able to connect a bunch of various devices. And the bridges here that I mentioned basically allow the translation between the signals from the AHB to the APBs. So I'm going to refer to them as the host buses and the peripheral buses because it's going to make it a little bit easier. It's the typical lingo I prefer to use. So our host bus is the one in grey. We've also got 2 other connections to these bridges. So DMA2 is connecting to peripheral bus 2, and DMA1 is connecting to peripheral bus 1. That allows the DMAs to be able to access those peripheral buses without tying up the host bus, essentially. We'll also notice that the host bus is also connected to our GPIO ports, which is good because it means that it's not going to have to go via the bridges in order to be able to toggle pins and do that sort of stuff if we're just doing sort of standard GPIO input or output. So that's kind of how you'll find most of the various components within most STM32 devices in the family connected. So you'll have most of your faster stuff connected to a bus matrix. You'll have a host bus, which is connected between the bus matrix and the bridges, which then go off to the peripheral buses. And in most of the devices, except one that we're looking at here today, there's only 2 peripheral buses that you'll have to deal with. You've typically got APB1, which in most of the devices is going to run at half the maximum speed of the CPU's maximum. So in this case, maximum 50 megahertz for APB1. And then we've got APB2, which can operate at up to 100 megahertz. And connected to either of those, we've got a selection of different peripherals. There is commonalities there as well, so you typically find the analog to digital converters are going to be connected to the peripheral bus 2, and you'll normally find those guys down the bottom left of the diagrams. And then it's handy to be aware of, if you're using a particular peripheral, which bus it's actually connected to, because that can, depending on your clock selections for that peripheral, can determine what clock rate that peripheral is actually going to be operating at as well. So for example, if we were using the USART1 peripheral and we were obtaining its clock directly from the bus, it's going to be receiving 100 megahertz clock. Whereas if we were using USART2, which is connected to APB1, then in the case where it's getting its clock from the bus, it's going to be receiving a 50 megahertz clock if those buses are running at their maximums. And those buses can, to certain degrees, be don't necessarily have to be run at their maximum, depending on how you go and configure the clocks, and the various prescalers and things like that will determine what those clock rates will be on the buses. We'll go into that a little bit more when I've got a video coming up where we'll actually be looking at the reset and clock control, or the RCC, in a bit more depth, and sort of clock configuration and things like that as well. But the main goal here was so that people can become a little bit more aware of sort of the interconnectedness of the various chips. So that's the diagram for that one. In most of the data sheets as well, you're also going to find the bus matrix diagrams. So in this case, we only have the one matrix. And we can see here the iBus, DBus, and SBus from the Cortex-M4 CPU. We can see our connections from the DMAs, and then we can see our various connections over to the right here. So we've got our master connections on the right-hand side and our slave connections across the top. And then each of the little dots indicates that it's possible for the matrix to create a connection between various points. So for example, if we look at our iBus, or our instruction bus for the CPU, we can see it's capable of retrieving data from either port M0 or our I-code connection to our flash memory, and it's capable of connecting to our SRAM to be able to pull instructions from our SRAM. But the CPU is not able to pull information via the decode connection to the flash, because that's specifically meant for data. It's also can't pull instructions from either our AHB1 or AHB2 connections either. So depending on what each thing is needing to be able to access will determine what connections are possible for it within the bus matrix. Much as we can see, say for the DMA MEM2 connection, except for the I-code connection to the flash, it's capable of accessing basically everything else. So it can access the flash via decode. It can also access the RAM and both AHB1 and 2. The DMAs also have the other connections that we saw in the diagram, which connect directly to the peripheral buses, or to the bridges to the peripheral buses, so that they're able to get access to that without having to affect the host bus and without having to access them via the bus matrix, which makes things a little bit more efficient as well, which is why it can be beneficial to make use of DMAs, which is again something that we're going to be looking at in a video coming up. So that's that one. That's the F411RE, which is on our Nucleo board. The next one we're going to have a look at, we're just going to compare them as far as similarity. So the next one we're going to have a look at is still an F4 device. This is a F407. And this is a discovery board. Turn it up the other way. So board's upside down, but the chip's up the right way. And if we jump over to the diagram for that one, which is this one here, and we can see it's really quite similar. However, the 4.0 series of devices, which includes the 407 has the potential to have a lot more peripherals, a lot more GPIO ports, and a few other additional peripherals which are connected to the bus matrix, but overall the architecture of the chip and the way things are connected is basically identical. So we've still got our bus matrix, which has all of our higher speed stuff connected to it. In this case, we also have a second USB, so we've got the high speed and the full speed USBs here. We've got a camera interface, random number generator, FSMC for connecting to various other memories, and we've also got the potential to have Ethernet. Now, some of those features aren't available on this particular device. One of the other handy things in the data sheets as well, if we scroll up a little bit, is this particular table, which tells you for all of the devices that this document is directed at, what particular features are contained in there. So they all share the same number of timers, for example. They all have the internal watchdog and windowed watchdog and a real-time clock. But if we go to the second part of the diagram, we can see there's a distinct difference in between the number of GPIOs they have and some of the other peripherals as well. So we can see some of them don't have a camera interface, some of them do. In this case, the particular device that we have is the 407V, which is this guy here. So in this case, we do have a camera interface on this one. We can see it's got 82 GPIOs, 16 analog to digital channels. So it's handy to be able to find that particular information as well. Also lets us know we've got a possibility of 0.5 MB or 1 MB of flash memory, how much RAM we've got, that sort of stuff as well, depending on which particular device. But overall, the architecture and the way the buses are connected is fairly similar. This one does have a third AHB bus, or advanced high performance bus. So this one giving it access to the memory controller, and then AHB2 in this case doesn't just connect to USB, it also has the connection to the camera interface and the random number generator. But other than that, fairly similar, just maximum clock speeds are slightly different. So rather than a maximum of 100 megahertz for our CPU, we've got a maximum of 168, and our speeds for our buses reflect the various maximum speeds. Again, APB1 here, in this case, maxes out at 42 megahertz, whereas APB2 maxes out at 84 megahertz. So half and a quarter of the maximum CPU speed respectively. But in this case, all of the AHB buses are capable of running at full CPU speed, up to the maximum of 168 megahertz. So fairly similar, some slight differences between the F411 and the F407. Let's go down the family a little more. Let's have a look at the F103 C6. So this is one of the ones that you'll typically find on a blue pill. You'll normally find either the C6 or the C8 on a blue pill board, which is one of these guys, if we pull that up on the camera. So that's one of these. So not a lot of GPIO on that one. Smaller chip than the other two, but still a very similar architecture. In this case, it's running an M3 CPU rather than the Cortex M4. It has got a maximum of 72 megahertz. Still connecting to the bus matrix. You'll notice there is a difference in the fact that the instruction bus is actually connected directly to the flash rather than going through the bus matrix on this device. So a little bit of a difference there. There is a bit of a difference in the fact that the DMA here doesn't have a direct connection to the AHB to APB bridges on the diagram. if we have a might help if I don't go changing which scene I'm in OBS. If we have a look at the actual, don't know if we have a, doesn't look like we have a matrix diagram for this one in this data sheet. So on this one, we've still got the similar thing with the APB1 and APB2. So APB1 is capable of running at up to half of the CPU's maximum speed, while APB2 can run at up to the full maximum speed. But overall, fairly similar architecture. Of course, because it's got less stuff built into it, there's less things connected to our peripheral buses, and we've got less things being connected to our bus matrix. If we go down to our F0, which is have a little development board for that one, which is kind of like the baby of the family of all of the ones that I have. That's this little guy. So again, smaller chip. And in this case, we're running the Cortex M0 CPU, which goes up to a maximum of 48 megahertz. We've got less connections shown between the CPU and the bus matrix, but there is also a few other details which are missing from this diagram that we'll find on some of the others as well. So it may just be that there's a little bit of oversight there and there is actually some things missing, or it might just be that there is only one connection between the CPU and the bus matrix in this situation. Again, this document doesn't actually have a bus matrix diagram that I'm aware of. No, it'd be in that section there somewhere if it did. Doesn't actually specify the speeds, maximum speeds for the peripheral bus 1 and 2, but it's still going to be peripheral bus 1 on the right-hand side and peripheral bus 2 on the left-hand side, and it's likely that peripheral bus 2 is running at a higher clock speed. So again, similarities there. One of the differences here is that our GPIO ports aren't hooked up to the same AHB as goes between our bus matrix and our APB bridge. It's actually got its own separate connection to the bus matrix, and it's got a AHB decoder there, which then gives access to the GPIOs. Part of the reason why I'm covering a lot of this stuff is because, especially when you're having multiple different parts of the system transferring data in different ways at the same time, it can be handy to know which connections are where, because there's no point having, say, the CPU and a DMA accessing a certain thing if they're both having to fight for access to something via one of the buses or one of the bus matrices or something like that. Like, for example, if we jump back to our F411 diagram, say we have the CPU needing to continuously access USART2, it's having to go via the bus matrix and then AHB via the bridge to APB1. If it's regularly accessing that and streaming a decent amount of data, and then we go to get, say, DMA1 to start sending or receiving data through, say, one of the SPIs on that same bus, then that's going to mean increased traffic on APB1. And in that situation, it might be worth, depending on how much congestion there is on that particular bus, maybe worth actually not using one of the SPI peripherals on APB1. Might be worth using one of the ones that's on APB2, so that you're actually spreading the load and not clogging the buses up as much. So it can be handy to be aware of that. The next one up from this that I have in my collection is the F429, which is really quite similar to the 407 and the 411. Same kind of layout, in terms of the bus matrix, just has more connections because there's more hardware, and the way the DMAs and the AHB connect to the bridges to go to the peripheral buses is all the same. It's just the peripheral buses have more on them. So the example for that one is this particular board. So zoom out a bit and we'll have a look at that one. So that's this Discovery board. Get that one out of the road, which the chip for that one's actually on the back along with the SD-RAM. And that does have a lot more GPIOs and peripherals than the F407 or F411. Things change a little bit when we go to the next one, which is hiding. See if I can grab that. One of the ones I didn't actually get out earlier. Let's have a look at this one. So that's this guy, which is also a Discovery board. Just fix that light up there, which is the F769i Discovery board. This one's pretty dusty. Unfortunately, both of my offices tend to get pretty dusty living in the country. And we can see underneath the wiring, the actual chip for this one is the BGA package just there. So the F7 series tends to be a tiny bit more complicated than the F4 series. We're running the Cortex M7 processor on this one rather than the M4. And this one is capable of up to 216 megahertz. We can see there's additional connections here. And we've also got an AXI connection, or AXI, which is a more advanced bus than the AHB. So the Advanced High Performance Bus, or AHB. And then more advanced than that is the Advanced Extensible Interface, which is another form of connection that was developed by ARM, which you'll typically find quite regularly in ARM processors for smartphones and that sort of thing, where even more performance is required from the bus, more features and things like that. So you can see in this case, there's 11 slaves and 8 masters going to this AHB bus matrix. We've also got a little system here to be able to convert between the AXI and the AHB based bus matrix, sort of to translate that. And then the rest of it's still fairly similar to what we're looking at for with the F4 devices, where we have our AHB1, which is then connecting the bus matrix to our peripheral bus bridges. And again, our connections from DMA 1 and 2 going to our bridges so that they can access peripherals without having to use the bus matrix or AHB. So again, fairly similar. Just a few more bits and pieces, more peripherals again. Things start to get a little bit more complex when we look at the next one, however, which can be a little bit of fun to program with if you don't sort of sit down and get a good understanding of how the buses are connected. So this guy is this one. And this one is a Nucleo board, but it's running the H743Zi chip. So no longer in the F series. This is the high performance series. And if we have a look at the diagram for that one, looks something like this, which has a lot more on it. And especially when you start to deal with DMAs and things like that, things get more complicated pretty quickly with this if you're not careful. So we'll notice one of the biggest differences here is that there's actually 3 bus matrices on this device. So we've got a 64-bit AXI bus matrix, which is connected to the CPU. CPU also has an AHB connection over to our 32-bit AHB bus matrix. All of our flash and our AXI SRAM, as well as our memory controller and quad SPI and some of our higher performance stuff, is all connected through the AXI bus matrix, which allows it to have more performance. Then the next sort of speed grade of peripherals are then connected via our AHB bus matrix up here. So things such as our USB, high speed and full speed, our second STMMC. So we do have an STMMC connected directly to our main bus matrix, but we've also got another one over here which is connected to this one, and then our Ethernet there. Now we'll notice that there's one DMA connected to this bus matrix, our MDMA, whereas our DMA 1 and 2, which we're used to from the other devices, are actually connected to this bus matrix. And then we've got various connections between this bus matrix and this one, as well as the connection directly from the CPU to this bus matrix. This one then goes off to a connection directly to this peripheral bus here, which is APB1. So that one is connected basically directly to that bus matrix via the AHB to APB bridge. However, our APB2 is connected directly to that as well via a different AHB bus, so AHB2. So a little bit different than the architecture on, say, the F4, where we have one AHB connecting both of those peripheral buses. This has a separate AHB for both of those peripheral buses, and then we have another AHB which is going between this bus matrix and this bus matrix down here, which is another 32-bit AHB bus matrix. This one has a connection to both of these, as we can see there. And this one then provides a connection via another AHB, which is where we then see the connection to our GPIO ports and our ADC3, and that then goes off to our fourth peripheral bus. So this is APB4, and this is where we now see things like the real-time clock and some of the low power peripherals connected to that one. And we also have a third peripheral bus, which is hiding at the moment, which is over here, not shown that well on the diagram, but we've got AHB3 here, which goes through an AHB to APB connection, and this grey line here going off to the LCD TFT and windowed watchdog is actually our third peripheral bus. So much more complicated. And peripherals are connected in a way that you can kind of leverage different levels of performance in a way that you can't with some of the smaller devices. So we can see we still have 3 analog to digital converters, much as we do on, say, the 769 that we were looking at. If we scroll down on that one, ADC 1, 2, and 3, which are all connected to peripheral bus 2. On this one, we've got ADC 1 and 2. They're actually connected to AHB1 rather than to a peripheral bus. And then ADC 3 is actually connected to this AHB down here. So in order for, say, the CPU to access that one, it's actually got to go via 2 bus matrices, this one and this one. For these guys, it's got to go through, can use its direct connection potentially to access this bus matrix directly and then go to ADC 1 and 2. So the other thing to note here is there is a 4th DMA in this device, which is our BDMA, which is connected directly to this bus matrix. So 4 different DMAs, not including our DMA 2D, which is technically a 5th DMA, but we have DMAs connected to each of our 3 bus matrices, so we can actually leverage those to get better performance by spreading the load or data congestion across various parts of the chip in order to be able to make best use of the hardware. So that's a bit of a look at how the various different devices connect their peripherals together and the various different components. So looking at the diagrams, you start to realize that although the microcontroller has a CPU, it's not necessarily the biggest part of the system in terms of the amount of different parts it has. In terms of the amount of silicon it takes up on the chip, that's one thing, but in terms of the amount of different peripherals that are actually connected to that and the ways that they're connected, there is potentially a lot more to it if you choose to dig into it a little bit. So if you've got a device that's different than the ones we've looked at, or even if you've got one that's the same, it's worth downloading the data sheet. And you'll typically find this diagram fairly early on in the data sheet. You'll notice most of them, like page 19, page 24. It's fairly easy to open it up and just page down a little bit, and you'll find the diagram fairly easy. It's pretty easy to spot. But have a bit of a look and see how things are connected. If you've got your data sheet contains, let's actually have a look at this one because we haven't seen that so far. We scroll down a little bit and we'll see the bus matrix diagrams. So because this one has 3 bus matrices, it shows all 3 on those diagrams. It's good to be a little bit more familiar with how various parts are connected to each other, what different pieces can actually access different other pieces of the system, especially in situations where, say, if you're dealing with doing audio or streaming video data from a camera or things like that, and you want to get DMAs involved, it pays to have a bit of an awareness of where things are connecting, how much data you're trying to push through particular buses, things like that. Like, for example, on the F769 iDiscovery board with the bigger touch screen, there's certain situations where if you're getting the LTDC peripheral to push a huge amount of data from RAM to the LCD screen, but you're also trying to do things like audio processing and things like that and get the CPU to be processing data while you're streaming audio data with the DMAs, you can get into situations where you will start to see things stutter. And it's not because of the CPU itself is being overloaded, it's because you're starting to overload buses. And that's something that I have actually come across before, and using the diagrams and having an understanding of how the various buses and the matrices and various components connect together, you can try and find workarounds and leverage more performance in order to avoid those sort of situations. So hope you find this interesting. I personally find this stuff really fascinating. I'm always keen to understand how the internals of the chip are actually working. I guess that's why I enjoy working with FPGAs as well. But if you like this one, love it if you hit the like button, subscribe to the channel if you haven't already. There is also other ways to support the channel, such as Patreon. Big thank you to up that corner to Craig and Luther, the first 2 patrons for the channel. If you'd like to help support the channel, then the Patreon link is down there. If you've got any questions about this or comments or feedback, anything like that, feel free to leave a comment under the video, or you can also jump onto our subreddit there and let me know there if you like. I do try to keep up with the comments and stuff like that, answer any questions, and I do appreciate constructive feedback as well. And if you'd like to check out any of the code from some of our previous videos, we do also have our GitHub there as well, if you'd like to have a look at that. So thank you to all of our recent subscribers and all the people watching the videos. It's great to see people have been enjoying them, and hope you enjoy this one as well. So thank you for watching.